Hi, so this is going to be the lesson on acidic and basic salts. So we'll not be doing the homework, but since we didn't have a PowerPoint technically for this lesson, we just made a note copying from the board. I will be using the textbook as a sort of medium, let's say, to help me explain what basic salts are. So this covers a little bit right after the Ka, Kb values, and we'll be skipping ahead to Unit 9, and we'll come back to buffers and titration curves in the next class or next video. Additionally, all the homework will be done on a separate video, so this is just the explanation video, so to speak. So the important, as it says here, there's an important relationship between Ka and of an acid and the Kb of its conjugate base. So if you write this is this derivation that we did go through in class. If you write our Ka expression for acetic acid, you get acetate ion times H3O plus divided by acetic acid. And if we write the similar expression for acetate ions in water, these acetate ions, when added to water, these acetate ions are going to act as a conjugate base, except the proton from water form acetic acid and OH minus. So it's very similar to this equation, except it's the reverse A, and B, the H2O and H3O plus are replaced with H2O and OH minus. So we write our Kb from this expression, and then our product Ka, Kb, turns out when you multiply them, you cancel out the acetate concentrations, and you're left with H3O plus times OH minus, which we know already from before is Kw. So essentially, what this means is whenever you take the Ka of any acid, you multiply that with the Kb of its conjugate base, you always end up with a constant, 1 times 10 to the negative 14. And what that means is if I give you the Ka of acetic acid, you can find the Kb of acetate, even if it's not given in the back of the textbook or that's not explicitly stated, just by doing 1 times 10 to the negative 14 divided by Ka. Likewise, if I give you the Kb of ammonia, you can find the Ka of ammonium ion, which is a acid, right? Even by that Ka would just be 1 times 10 to the negative 14 divided by the Kb of ammonia. So that is a way that we use to calculate Ka or Kb of conjugate acids or bases. And where do we use Ka, Kb of conjugate acids and bases is primarily when we're working with the salts. As it said here, a soluble salt of the conjugate base, such as sodium acetate, forms acetate ions in solution. We can't really buy a bottle with just acetate ions. Those don't exist. So ions, when you have a negative ion, you intrinsically always need a positively charged ion to go with it. So conjugate bases and conjugate acids usually are in the form of salts. So we'll talk about what a salt is and compare strength of acidic. So we're going to skip all this for the time being. We'll come back to that imminently. And we're going to go to acidic and basic properties of salts. So a salt is the basically the product, one of the products, the main product at least, that you get from a titration or an acid-base reaction or neutralization reaction. But all salts are not neutral. So we learned before, you might have said like, okay, HCl, NaOH gives you NaCl and H2O. NaCl is a neutral salt, but not all salts will be neutral. And that's kind of important to know. So here, we're going to look at neutral salts, or salts that form neutral solutions. And these are formed from the reactions between a strong acid and a strong base. So for example, I think if we'll go to the next page, I'll write that here. If you have a reaction that involves again, remember that the salt is formed from a acid-base reaction, correct? So a strong acid example is HCl, strong base is NaOH, and when both of these react, they give us NaCl plus water, right? And this is a neutral salt because both of these are strong, A. And B, if we look at the reactions in water, so when I did do this reaction, I have the Na plus ion and the Cl minus ion. And if I write my, expressions out, HCl plus water, what did that give me? That gave me, well, this arrow, H3O plus Cl minus. So this is the conjugate base of HCl. So Cl minus acts as a base in water. So hypothetically, this would be the reaction that I would get. It's almost the reverse of this reaction up here. But this reaction does not occur. You can basically like no reaction because I can never form HCl as part of my products. HCl dissociates completely to give Cl minus and H plus, which combines with this OH minus here to give you water. But essentially, Cl minus plus water is going to give me no reaction. And that's why it doesn't really form OH minus ions in water. It's a super, super, super weak base. Similarly, if you look at NaOH, this plus water, the reaction was NaOH plus water, giving us Na plus OH minus. I don't really need the water. This is just to make sure that this was an aqueous solution, because the hydroxide just splits apart into its ions, which is basically Na plus and OH minus. And again, this is the conjugate acid of the strong base. Right, Na plus is the conjugate acid, which means it should react with water to donate, and it should form in some ways H3O plus. It should give us charge in water to form H3O plus NaOH plus H3O plus is, let's say H plus because that makes better. So water we know is HOH. Na takes this OH, or water I should say. I don't even know how this works. How does this work? It's the reverse reaction of this, basically. Your Na ion is attracting your OH minus ion, which leaves H plus ions in solution, which could create an acidic solution if I was not also forming a strong base in my products, which is impossible. So this is also a no reaction situation, because I cannot form NaOH or HCl in my products, right? So this reaction lies pretty much entirely to the left with the Na plus ion. So they don't react in water to give me anything, and therefore they're not acidic or basic. They're just neutral salts. So Na plus and Cl minus form neutral salts, right? And you can also just look, I formed NaCl from HCl and NaOH, so that was a strong acid, strong base combination, and therefore will be neutral, right? So acidic and basic solutions. Here we go. Hydrolysis. Okay. Let's take this example, for example. So here we have, let's do the example where we have a strong base, strong acid plus a weak base. So this is, ammonia is a weak base, so we'll use that here. Strong acid is always HCl, standard. And this is going to react to give us NH4Cl plus the water aqueous medium that it's in, right? So here, interestingly, again, we can split apart this salt. So this is a salt, right? This is a neutralization reaction. Acid plus base, this gives us a salt. And we can tell, because it's a strong acid plus a weak base, the acid part wins out because it's stronger, and therefore this will be a acidic salt. But if we want to write the equations for it, we would write NH4 plus could react with water to form NH3 plus H3O plus. And Cl minus, as before, does not react with water because you cannot form HCl in the products, right? So this is basically a no reaction. The equilibrium lies all the way to the left. So that reaction basically does not happen, but this reaction does happen, and I do get H3O plus ions in solution, so this makes the solution acidic. So NH4Cl in water is acidic, right? Because the Cl minus doesn't contribute, NH4 plus does contribute to solution and it generates an acid. So this is what creates the acidic part from a strong acid and a weak base titration, or a neutralization reaction. And similarly, the exact opposite is true of a basic solution. I don't really have a place to write this, so I'm going to write this down here. A strong base plus a weak acid. So for example, NaOH plus acetic acid in water is going to give me sodium acetate plus water, right? So here, again, interestingly, I know that the combination of a strong base and weak acid is going to give me a basic salt, just because the base is stronger here. And this can be proven by writing what the ions are and how they react in water. So sodium acetate is going to dissolve and split into its ions just because it's soluble, right? And the acetate ion is going to react in water to give me acetic acid plus OH minus, right? And this OH minus that contributes to the basic nature. Na plus plus water, we've seen before, basically results in a no reaction, because this is a conjugate acid of a super strong base. Therefore, it's a super weak acid. So therefore, it does not react in water to give any reaction. Because if I were to write a product, it would be NaOH. I know I can never write NaOH as my product. So I have to have, this is no reaction. So the only source of pH or pH change in my reaction is this OH minus, which comes from this ion and not this ion. So Na plus over here, the Cl minus up over here are called, there's basically spectator ions. They don't contribute to my pH whatsoever. Right, so now basically we will briefly look at a Ka-Kb reaction of something else. So I'm going to do what happens when, you know, a weak acid reacts with a weak base. So for example, let's say that weak acid is methanoic acid reacts with ammonia, right? And this is going to give us the salt NH4COO minus, or HCOO minus, right? So NH4 plus and HCOO minus together form the salt NH5COO. And we're going to split that into ions, because we're going to write what happens to both these ions in water. So HCOO minus plus water is going to give us HCOOH plus OH minus, whereas ammonium in water is going to give us ammonia plus H3O plus, right? And now we have both of these reactions are possible. We have both OH minus and H3O plus in solution. Basically, we have to compare, we have to see which one is more. So we have to compare the Kb of methanoate ion and the Ka of ammonium ion. So how do I find the Kb of HCOO minus? I do 1 times 10 to the power negative 14 divided by Ka of methanoic acid, because we just went over that, right? And if I do that calculation, the Ka of methanoic acid turns out to be 1.8 times 10 to the power negative 4. So 1 times 10 to the power negative 14 divided by 1.8 times 10 to the power negative 4 gives me 5.5 times 10 to the power negative 11. And the Ka of ammonium is 1 times 10 to the power negative 14 divided by Kb of ammonia, as we just went over. So 1 times 10 to the power negative 14. Kb of ammonia is 1.8 times 10 to the power negative 5, which is If I have a -5, that would just make that one small. 5.5 times 10 to the power of -10. And so we can see that the Ka of ammonium is greater than the Kb of methanoate. So I'm going to say that again. Ka of NH4 plus is greater than Kb of HCOO minus. And we know that, again, the K value gives us the extent of the reaction, or how much products are formed relative to the reactants, right? It's the equilibrium. So at equilibrium, is there more products, is there more reactants? And the higher the K value, the more products there are. So here, ammonium is going to produce more H3O plus than methanoate produces OH minus. And therefore, it is a slightly acidic solution because the Ka of ammonium is greater than the Kb of methanoate, right? So that's how you compare them. And if we do it the other way around, if we take another example, we can also, there can be the opposite, right? If my Kb is greater than Ka of my conjugate, remember I have to find the Kb of my salt and the Ka of my salt, or conjugate base and conjugate acid. Those Kas, if you compare, if Kb is greater than Ka, the solution is basic. So the other way around. I'm not going to work through that example. I'm not going to give you a question where this even shows up. This would just be like a multiple choice kind of question. But yes, that's how you calculate it. And there was an example for you. So here we will look through sodium fluoride. Acidity, basicity. This is going to be, I'll go over that in homework. But here is an interesting chart that kind of shows you the relation between Ka and Kb. So we see that a strong acid has a high Ka. Its conjugate base will have a super low Kb, like 10 to the power -20, right? Because this Kb, it's not even it's 10 to the power -20 Kb. So there's no products being formed. It's entirely to the reactant side. So this does not essentially react with water at all. But any weak acid-base pair, so let's say take ammonium, its weak acid conjugate is ammonium. I said that wrong. Let's take ammonia as a weak base. The conjugate acid ammonium is also weak, but it's an acid, of course. Let's take acetic acid. It's a weak acid. Its conjugate base is also weak. And it's not super weak like the chlorine. It's just regular old weak, which means we can calculate a Kb or Ka for a conjugate, and that actually has 10 to the power negative. It might be small, like -10, -11, but it's not, -20, which is like a million times less strong, right? Or even more than that. Cn minus is a base, and we have a conjugate acid, both of which are weak, right? So that's why it's important to look at this, and I think it really helps understand that the strong goes to super weak, ignorable. The weak just goes to another weak. So weak interactions, so weak stuff are important, right? So that's that. And then we can skip all this, and I think that was basically it, and I'll go over the homework. There's a couple of homework on the stuff that we just went over, and some homework over here, I think. Yes. And of course, we have to do titration questions, so that's going to take a while. And so I will sign off and see you later.